Okay, guys, today and tomorrow, I'm just going to focus on a part of the lesson that initially I was planning not to have it for this term and let it go, but because it is a very important one and we have also enough time, I decided, okay, let's cover that. But that's very important in terms of the concepts that we learned before in the trigonometry. Just today and tomorrow, from Monday, we change the gear. The reason I'm just trying to work these ones because the importance in all areas of the math, specifically when you go to the advanced function, more importantly, when you just go to the calculus function, then that is a good idea. You get to have a small taste of these kind of things that we have done before. Okay. Now, initially, when I'm just going to start, I'm going to talk about the thing that we covered that in many sessions ago while we were still at the Berkshire and inside the class, we talked about the inverse of a function. You remember that based on the things that we learned, we said that, for example, imagine this one, it's, guys, do you see what I'm drawing, or is too much light, less light? How it can be improved? Do you see my drawing, or no, there's too much light?
Yeah, I can see it.
Okay, is it fine? Okay. We said that if this is going to be, for example, we said that if this is going to be, this is a subspace of the R real numbers. By the subspace, I mean you go to the all real numbers and take a whole feast of it. For example, imagine that you want to grab a bite, you take some part of the real numbers and you call it, it's going to be the domain of your function. And you say that, okay, the other subspace on the other side, it becomes the range of my function. Okay, and based on the thing that we learned, we saw that if we had a member, I call that member A, inside that domain, we came to find that we can find the transformation which it takes point A, bring it somewhere inside the range, another subspace. We call that, if we call that transformation f of x, then we said that, okay, that point inside the other subspace, it becomes f of a. That's what we learned. And that's what we talked about that. Then we were working with the inverse function. And more importantly, we saw that this transformation has a kind of a direction. What did I mean by the direction? I said that, for example, if we are with the point A, and we are ending up with the point f of a, the direction of this transformation is somewhere like that. You move something from the domain, leave it, place it at the range. But also, the other thing that we did, specifically for a couple of weeks ago, we learned the concepts of the inverse of a function. What was the concepts of the inverse of a function? The concepts of the inverse of a function was this, that it starts from some points in the f of a. From f of a now, we just move back to the same point initially. And you learn that we call that what? F inverse of x. And we saw that while we were talking on the inverse of a function, that f minus 1 of the x, minus 1 is not an exponent, it's not a power. It's a symbol, which that symbol allows you to know that the function is being reversed. By the reversal, I mean that you move back the path which you had taken. And that's what we talked about, the inverse of a function. Now the direction this one is going to be backwards. The function is a transformation forward. It takes you from the domain to a range, but for the inverse of a function, it's backwards. It takes you from the range inside the domain, right? Okay, for example, guys, imagine that there was no case for the coronavirus. and you had to go to the Berkshire school. Imagine there is a taxi who takes you from your home to the Berkshire Academy. It becomes a function itself. The path which you take from your home to the college is a forward transformation. You move from home to the college. But when your classes are done, you want to go back to home, you take another taxi. The taxi takes you back from the college to your home. It becomes the inverse function. You see, the path which you have taken, it becomes reversed. Home to college becomes now college to home. That's what we call the inverse function. And give me 1 second, bring a glass of water for myself. Okay, that was the first thing that we discovered about that. And if you remember, as an example that we did, we developed a kind of an algorithm in order to find the inverse of a function. And the inverse of a function, followed 3 steps. Imagine that. I'm just going to give you an example. The example which I'm going to give you is going to be this. I say that the forward transformation, which I call that f of x, simply is given that as x squared. You see, guys, what I'm writing? Is it blank? Is it too much light, or it's fine?
That's fine.
It's fine. You can see that?
Yes.
Awesome. Then we say that, okay, if f of x is x squared, it is going to be our example. We said that we have a forward transformation. By the forward transformation, what did I mean? I meant that we have f of x, this function, this transformation, it takes something from the domain, leave it at the range, and how it transforms it, it squares that member of the domain. We said that, if you remember, from the things that we talked about, the inverse of a function, we said that in order to find the inverse of a function, the thing that we do is we follow a couple of steps. The first step was this. Step number 1, if you remember, we said that we do replace f of x with y. We say y becomes x squared. It was step number 1. For step number 2, we said that we move backward, we move from left to right. Wherever we see y, we name it x, and wherever we see x, we name it y. I move from back to right, from left to right, I see y, I'm going to rename it to the x. And I see x squared, I'm going to rename the essence of the x to y, which becomes x equals to y squared. Okay, it was step number 2. Let me write that. If this one was step number 2, step 2, it was step 1. And now, the other thing that we did was this. We said that when we are doing this, we said that the next step, step number 3, was to express y in terms of the x. I said that in the examples which we covered in the class, we noticed that we have to take every item which is y to the left, every item which is x to the right, and we simplify that to a point that y becomes only with coefficient 1 and exponent 1 to one side. And now I see the coefficient is 1, but the exponent is 2. In order to transform the exponent to 1, I take the square root from both sides. It becomes y equals to what? Equals to square root of the x. Now, this one was called step number 3. Step number 3. For step number 4, we said that for step number 4, we have to rename y with f inverse of the x, which is an easy step. I change y into f inverse of the x equals the same thing expression which you had to the right side, which is going to be the x. It was step number 4, correct? That's essentially, it's a review of the thing that we did that many days ago when we were working with the inverse of the functions. Guys, it's a review. Do you have any questions from this?
No.
No? Okay. However, we came to a very good conclusion that we said that we reviewed two properties of, before I just do that, before we review three properties of the inverse of function. The first very important property, guys, that you are gonna use that today, and it is very important, is this property. And we're gonna rely on that today a lot. Please listen to that. If the transformation is forward, I mean you move from the domain to a range with the forward transformation of f of x. If you move backwards, your domain becomes your range becomes your domain. Everything is inverse, everything is reversed. For example, with the case that I said that you move from home to college, if home is your origin and college is your destination, when you move back to home, now your college, which was initially your destination, becomes your origin, and your home, which it was your origin, becomes your destination in your trip. And that's the same case for this. When you have an inverse transformation, your original range becomes your domain, and your domain becomes your range. This is very important. The other thing that we talked about the composition of these functions. We said that there is a very important property. I'm just going to do that by the example which we did. We said that, for example, in our case, if f of x is square x squared, and if f inverse of x, as we got, it becomes square root of the x, we drove a very, very important property. We said that the composite function is what? The composite function is built in two different ways. Either laptop is very slippery today. Okay, you have a good view now?
Yes.
Yeah. We had two important property. We said that f of, we call that f o f minus 1, which is essentially f of, imagine f of x, f of inverse of x, which in our example was what? In our example was, we have f of x, I put square root of the x inside the x. Then it becomes what? Becomes square root of the x to the power 2. Then we got it to be x, which it gave us to a very good understanding that this property is valid, that we're going to derive it, that f composite f inverse, it is always x. You remember that, guys?
Yes.
Yeah, it was one important property that we derived that when we were working with the inverse of the functions. Also, we had one other thing. We said that, how about this one? Composite of f minus of f, which is essentially f inverse of f of x. Becomes what? We take square root of the x under this one. We got this one becomes this identity, because this expression, which it becomes essentially again, it becomes x. Then we get to this important conclusion now that even composition of f inverse with the f also, it equals to x. These are two important properties. We are going to use that also today. Whatever we talk today, we are going to use that for the inverse of the trigonometric functions for the sine and cosine. When regardless of the form of the f, always composition of the f which is inverse is x. Okay, it's going to be page number 2. Okay. Any questions, guys? Nothing?
No.
We move on to the last thing that we want to talk about that. As a kind of a review. The other important thing that we remember from the relationship between a function and its inverse, it showed up itself when we plotted these two functions. What do I mean? Imagine that I'm now trying to plot the functions which I just got the inverse of them. It is going to be the y-axis. It is going to be the x-axis. And also, I have the line y equals to x, although it's not drawn with so much care, unfortunately. And what we saw here was that if I plot y equals x squared, and if I plot also its inverse function, which is square root of the x. Guys, you can see what I'm writing, or there's too much light?
That's good.
It's okay?
Yes.
Yeah, you see that, and also that's the origin. You see that, guys? That was the thing that we came to a good conclusion when we were working with the inverse of function. We said that if you plot a function with its inverse, you come to this point that you see that if the function is, for example, in our example, is x squared, which its inverse is square root of the x, these two functions are the inverse of each other. They are always symmetric with respect to a line which we call that y equals to x. And what did we mean by the symmetry is that, for example, each of these plots become the mirror image of the other one if you think that y equals to x is a mirror. You are watching yourself inside the mirror. It means that, for example, if you look at this point, its distance to the line f of x is equal to its distance to its image. These 2 points have equal distance. That's what we define as being a mirror image, and that's how we define in its simplest term when we talk about a symmetry between 2 plots, 2 graphs. One graph becomes the mirror image of the other one, and the line of the symmetry, essentially it works as what? Works as the mirror that these two are watching themselves inside the mirror. It was this important property of the function with the inverse, and always the mirror, it was always the line y equals to x. Any questions, guys?
No.
Everything is fine?
Yes.
How about you, Philip?
Yes.
Good. And now, okay. Okay, now Now it's enough for all the reviews which we have done. And now we finished the review. We are now going into a new lesson, a new concept. Just guys, please give me a couple of seconds. I come back. Please review your notes. I'm going to be back in 2 seconds. Okay, now we are back even stronger than before. Okay, I had to just put this one here with the right angle. Okay, now we are moving into a new lesson. And now we are going back to our very favorite function in trigonometry, which we talked about that, first of all, as a ratio in a unit circle, and then we extend that definition to a function, which is this one. If you remember, f of x becomes the sine of the x. It is our favorite trigonometric function because you remember initially, in order to define that, we constructed a unit circle, and sine of the x, it was a kind of a ratio in a unit circle, the ratio of the any points coordinates y with respect to the radius of that circle. And then we extended that definition to define, in general terms, stepping aside from a unit circle, and we define sine of x for any function when x can be any real number. Okay, based on the thing which I said, we talked of two important things of the sine of the x. The first question was that, what is the domain of the x? I mean, x can belong to what? To any real number, correct? Because the sine of x is now, it just made the giant leap to move from a unit circle going into a domain that all the real number can be defined with that ratio. Then as a result, we said that with the higher perspective, the x can belong to all the real numbers. Now, the other thing that we want to do is this. We also said that the domain of the function, f of x belongs to what? We said that their domain, guys, please, this one is very important. I'm going to give you a tricky question later. It relies on this, which I'm going to talk about it right now to you. We said that the f of x, it becomes what belongs only to a bounded interval, which is going to be -1 to +1. Because you remember that even in that unit circle, or even from the plot of the sine function, always the y, which is our f of x, was oscillating back and forth between -1 +1. Imagine the interval is being gyred by, I should say, the sine function. It moves either from -1 goes back to +1, +1 goes back to -1, and this continues forever. And that was a range that we talked about. But right now, when you want to define the inverse of a function, we are gonna just make a bounded interval of the domain of the function. Because x belongs to everywhere, when we define the inverse of the sine function, we see that, oh my God, we are not getting only one answer. We have to spend 1,000 years to count the angles which corresponds to our inverse function. We don't want that happens. We want to find a very limited bound, an interval of the domain, that it gives us only one unique angle in our inverse function. We don't want to spend hundreds of years to find the angles, because you know that around the circle, you can rotate around the circle for infinite number of the times. Then you can find infinite number of the values for one specific, I should say, value of the inverse function. In order to avoid this, I'm gonna crunch the whole R domain into a very small one, but with one condition. I want to make this small domain. I'm gonna write it here. I'm gonna write this small domain in a way which is gonna be symmetric. And that's the only condition which I have to make. I'm gonna crunch X to a domain as small as possible, which it involves only one angle corresponding to the inverse. You're gonna feel what I'm talking about in 2 minutes. But the condition which I have, it has to be, this interval has to be symmetric. In order to make it symmetric and at the same time small, I make this interval from minus pi over 2 to plus pi over 2. You can choose many other, I should say, symmetric interval, but this interval is more a kind of a convention, is more convenient form. It's very comfortable to go from minus pi over 2 to plus pi over 2. You see that, guys? This is minus. I hope that you have a good quality of seeing that. You see that? Yes, everyone?
Yes.
It's minus. And now that's that. Then as a result, I come here and I say, I'm not gonna define my domain as R. I'm just gonna erase it, but my domain for the sine of the X becomes between minus pi over 2 to plus pi over 2. Still, my range is the same. The range doesn't change at all. It is still between minus 1 and plus 1. Okay, and now, by saying that, now this is the time to find the inverse of the sine function. In order to do that, I'm gonna follow the 4 steps that we covered. You remember that these 4 steps for y equals x squared? Now I'm gonna follow these 4 steps, in this case for the sine of the x. But this time is gonna be even much simpler. You have only 2 steps to follow. In order to find the inverse of this function, what I'm gonna do, as before, I'm just gonna put f of x, replace it with y. Step number 1, y becomes sine of x. Correct, guys? It becomes step number 1. Step number 1. For step number 2, what I'm gonna do, I'm just gonna start from the left, walk to the right, and find wherever there is y, I call it x, and wherever there is x, I call it y. What do I mean? It becomes x equals to sine of y, correct? And now, it is step number 2. Step number 2. Okay, for step number 3, we have to do what? We have to find a mechanism that we have y on one side with coefficient 1 and the power 1, and express y in terms of the x in that way. But here, when we look at that, we see that y is bounded, is imprisoned by a ratio sine, And it's not as easy as what we did that so far for the inverse of a function, like y equals x squared, y equals any polynomials. This time, it's very different. We cannot do that. Then as a convention, we truncate. By truncation, I mean we shorten our 4 steps into 2 steps. And at this stage, we say that the inverse of the function, now y becomes the arc sine of the x. And that's gonna be the final step. Or let me write that also. We have 2 notations to write. I almost forgot to mention that. Either we can say y equals to sine inverse of the x, or y equals to arc, arc, sine of the x. Both of them corresponds to step number 3 and step number 4 that we were looking for in the conventional steps for the inverse of the trigonometric function. Then we see that these 2 identities, I'm just gonna highlight it. These are the points, these are the function that we call that we got them from the final step in order to find the inverse of the trigonometric function. Then as a final point on this, then when it comes to find the inverse of a trigonometric function, it is very easy now. You do not need to follow step number 1, step number 2, step number 3, step number 4, as what we did on the previous function. Wherever you have y equals sine x, its inverse is going to be y equals arc sine of the x, or sine inverse of the x. Then there is no need to take those kind of steps. Step number 1, f of x replaced by y. Step number 2, change x with y. Step number 3, express y in terms of the x. Step number 4, replace y with f of x. Forget about these steps. Only starts y sine x becomes y arc sine of x in its inverse. Does it make sense, everyone?
Yes.
Yeah? Okay, nice. How about you, Philip?
Yes.
Awesome. Okay, it's gonna be page number 2. Now, we are gonna do something very important now. I'm just gonna draw a table which it becomes a kind of a very good comparisons of what you are gonna do. Okay. Let me pick up a color. Guys, give me 1 second, please. Hold on a second. Give me only 1 second. Oh, Rose and Philip, you see these guys? You see what I've written?
Yes.
Okay. And now look at the first function. I'm going to talk about, we talked about that before. It was what? It was y equals to the sine of the x. It was a forward transformation of the x. And what was the domain of that function? We talked about that. When we talked, it was initially r, but we crunched it. We said it becomes, let's say, for example, between minus 5 pi over 2 to plus pi over 2. We said that it's going to be smallest bounded region for the domain. The domain is essentially R, but for our purpose, we crunched it into a symmetric small interval in the R. And what was the R? What was the range, guys?
-1 to 1.
That's fantastic. That's right. That's an interval which includes anything between -1 to +1. Fantastic. Thanks, Rose. And that was a thing that we talked about. And also, we come here to define the second type of the function that we learned today. What was that function? Inverse of this sine x. Its inverse, I'm going to write it as y. Do you see this color or no? This is too blank.
I can see it.
Okay. We said that the y is now sine inverse of the x or arc sine of the x. Sometimes I write sine inverse of the x. Sometimes I like how to write arc, but both of them are the same. One thing with two names. For this one, in order to find it, I'm going to remind you of the chart we initially had. What did we say before? We say that, guys, if you have a forward transformation and you make a backward transformation, the backward transformation was the inverse sine, the inverse of that function. And we said that what? We said that whenever your domain becomes the range in the backward transformation and your range becomes the domain when you make it the inverse, correct? That is a very important property of the inverse function. Now we are gonna see what do I mean. When I come here, I said that for the inverse function, Philip, are you still there?
Yes.
For the inverse function, which is sine minus sine, the inverse of the sine, we say that the domain of the forward transformation becomes the range. You see, the domain goes to become the range because they become reversed, right? Then the range of inverse of the sine becomes what? Becomes something minus pi over 2 and plus pi over 2. Then the range of the arc sine, it becomes this. And its domain becomes the domain of what? The range of its forward transform. Then its domain becomes what? -1 to +1. Correct? And that's a very important property. Any questions?
No.
No? Then you see that the range and domain of a forward transformation with a backward transformation is interchanged. The domain becomes the range in backward, and the range becomes the domain in the backward again. Does it make sense, everyone?
Yes.
Yeah. Okay. Now, the next thing that we're going to talk about is going to be a very important property Then when we are done with this property, I think it's going to be a good time to take a break, huh? It becomes 1 over that we have gone through. Okay. For this next property of the inverse of the trigonometric function, as I'm going to talk about making a composite function of the sine of the x and its inverse, its backward transformation. Previously, I also reminded you of this fact that the composite function of f with its inverse, or inverse with its forward, it always becomes x, regardless of the figure, of the shape of the function itself. Its transformation can be any form. It can be a very complicated function, but when you use that property, it becomes x. The composite of the function, its inverse becomes x. Now, by using this, I'm going to drive for you two very important identity. We are going to drive that and talk about that more, very much in future. Then we say what? We say that the arc sine we said that, okay, we say f of x is what? Let me write it in a different paper. We said that f of x is what? Sine of x. And we say that f inverse of x is what? Arc sine of x, or sine inverse of the x. It's clear for everyone, huh? Then we come to make these compositions, two composite functions. We're going to say that the sine of arc sine of x, which is f composite of f inverse, becomes how much, guys? Any guess?
X.
That's right, becomes x. This is, I should say, the first important property, because we learned as a general rule, Philip, that the function, its composite, its inverse, always is x. Right, Philip? That's that.
Yes.
Yeah? Because you remember that we showed that property. We showed that property here with the functions if the examples were x squared and square root of the x. We saw that property is valid. And when you just make these compositions for both of these functions, the composite of the f with inverse becomes x. Now, the same thing is valid for the sine. And also, the second thing that you are going to get is this, that you say that the arc, now the composition is with the inverse. With what? With the function itself. You say that the arc sine of the sine of the x becomes how much? X again, correct? Sorry. These are very two important properties that we are gonna have. Right? We call that property number 2 of the inverse of trigonometric function. These are things that's very important. You may end up with these expressions many times in different trigonometric identities and functions. But the good point is that wherever you see this kind of stuff, arcsine of the sine x or sine of arcsine of the x, you simply put it x instead, and you should be done, right? These are because these things are comparably they are equivalent to each other. These are very important things. Please always remember them, these two. Any questions, guys?
No.
No? Okay. And now, just I think that's gonna be a good time to take the break, huh? Yeah. We can take the break, quick break. Now it's time 12:11. Guys, please come back by 12:26. Huh?
Yes.
Yeah. I see you guys in 15 minutes then. Then enjoy your break. See you soon then. Hello, guys. Are you back?
Yes.
Great. I just put my stuff there. How about Philip? Philip is also back, huh? Okay.
Yes.
Fantastic. Okay, now, before, we covered the first two properties that I mentioned that it's crucial for the inverse of the functions, which essentially was the interchangeability of the domain with the range of the backward and forward transformation, and also of the composite functions of its inverse with the function. Before I just move on to talk about the symmetry, the symmetric property with respect to the y equals to x. Before I do that, I'm just going to do that before we finish the session today. But before that, I'm just going to give you two examples in order to make it more tangible for you that what do we mean by this kind of stuff. Look at this. We previously learned that, for example, if we say y, for example, imagine that we saw that the sine of pi over 2 becomes how much, guys?
1.
That's so true. It becomes 1. Let me write it here because I need more space. We said that the sine of pi over 2, it becomes 1. Correct? You see that, guys, what I'm writing?
Yes.
Okay, and now it is exactly the same thing without having any difference if I say that the sine inverse or arcsine of 1 equals to pi over 2. You see that? If you are given, for example, they ask you, what is sine inverse of the 1? You are coming to ask yourself, oh, wait a minute. What is the angle that its sine ratio equals to 1? Then you search it through your head. They say, oh, it's going to be pi over 2. And also the same thing. Imagine that based on the things that we have learned. What is going to be this? For example, I say that to you. Now, sine inverse or arcsine of square root of 2 divided by 2. What is this? It's essentially, it's as if before you think of the answer, it's as if you ask that question yourself. What is the angle that its sine, I say that the sine, I should say a notation. For example, it's going to be a box, which it needs to be filled with something. The sine of that something, which we are going to put that inside the box, is going to be how much? It's going to be how much, guys? It's going to be square root of 2 divided by 2. That's essentially what do we mean. And of course, the same thing is going to be here. The same, I should say, box in order to put your answer is going to be here. That's what do we mean by this stuff. Okay, then these two, I think, is the same thing. I say, what is the sine of that angle that its sine becomes the square root of 2 over 2? If I find that answer, I can plug that thing also inside this because these things are equivalent. What is the angle, guys, that its sine ratio becomes the square root of 2 over 2?
45.
That's so true. Thanks, Rose. Or pi over 4. That's right. If pi over 4 becomes also 45. And the same thing, I can put it here. Pi over 4, right? And now, also, let me see. And let me give you one more example. Okay, let me give you this one as a very last example for this section. We said that the sine inverse of square root of 3 divided by 2. How much is that? It's essentially giving this answer. What is this angle that its sine, it becomes what? Square root of 3 divided by 2. And the only thing which you need, I should say, a box to fill this with the angle that you are going to find. You see, you ask yourself, okay, inverse, sine inverse or arc sine or sine inverse of this thing is how much? If you ask yourself that question, it's always better to ask yourself this question, that what is the angle that its sine ratio becomes square root of 3 divided by 2? If you answer it the other way, you can find the answer much easier. What is that angle based on the reference angles which you have learned?
Pi over 3.
That's so true, Rose. Thank you. It becomes what? Pi over 3. Let me get another color. I'm going to write pi over 3. And the same thing is going to be for here. Pi over 3. We got the same thing, right? Okay, now, seems that we are just moving to the right thing. And I hope that everybody now got a kind of a good feeling that what do we mean by the inverse of a number. Everyone is okay right now? Any questions?
No.
No? How about Philip?
No.
No? Okay. And now, guys, remember that whenever you say that you have no question, it is my time to ask you a question. I'm going to ask you a question that you please solve this one. Find this, that the sine inverse of minus 1 over 2 equals to what? And that's your turn now. You have to solve this one. You say, just ask yourself, what is the sine of the angle you give it a try? That's become your, I should say, the exercise which you would do that. Sine of that thing becomes -1/2. Remember, there is a minus sign there. You ask yourself, what is the angle that its sine ratio, it gives you -1/2? And please let me know when you're done. Then we can solve this together.
It's -pi/6.
Fantastic. Thanks, Rose. How about you, Philip?
No.
No answer yet?
No.
Okay, just spend a couple of more minutes. Philip, you got the answer? Not yet? Okay, we give it 30 seconds more, then we solve that together. Okay. Let's do that together. Okay. Where is my tools? Okay, yeah, that's here. Guys, what period do you have after this class?
I have BOH.
Yeah, you have what?
BOH.
What is that?
Business leadership.
Oh, yeah, business leadership. Oh, interesting. How about you, Philip?
ESL.
ESL. Ah, okay. With Dr. Tar, huh?
Mm-hmm.
You're going to read a novel or no? Do you do different things?
Novel.
Novel. What novel you're reading today?
The Giver.
The Giver. Ah, okay. Is it not yet done?
Almost.
Almost. Nice. The Giver. Okay. Now, just Philip, in order to explain what is that problem and how that can be solved, I'm just going to quickly remind you of the things that we did it before. Did you solve it, by the way? We're going to just flash back to the things that we learned. We said that, okay, we said that previously, if we have a unit circle, Philip, which I have a circle, I hope that you can see that on the camera. Probably not, because the pencil is not going to be that much visible to the camera. But this is a circle with the radius 1 its center is coincident with the origin of my Cartesian reference frame. We talked before, Philip, that we can come to pick an angle alpha representing for a point which is going to be called x, for example, on that unit circle. And when the x is rotating counterclockwise, we can find the sine ratio of our angle corresponding to the x, which is essentially represented by the y coordinate of this angle. We have alpha, we have x, then now it becomes as what we see there. That's right. Then anywhere that the point x is localize itself, provided that this is confined on the circumference of this unit circle, it's gonna at the end find itself on its sine ratio is gonna be always the y, because r is 1. Because we defined sine of the alpha, it was the ratio of y divided by r. Because r in a unit circle, if this is r, the radius of the circle is 1, it's always represented by y. But at the same time, we said that, Philip, that if we just pluck the same angle, but we move clockwise. I mean, now it becomes now minus alpha, but you see, instead of we just rotate counterclockwise, we moved clockwise, and we point to this point, x prime. You see that here also, Philip, in order to find the sine of this, we follow the same thing. We find the projection along the y-axis, then y here represents the sine of the alpha, which is going to be minus y, because it's below the origin. Then as a result, what did we say before? We said that the sine of minus alpha, if alpha is y, it becomes minus y. You see that? Because it's below the origin. Does it make sense, Philip?
Yes.
Yes? Then as a result, at this stage, we come here to answer the same question. What is the angle that its sine ratio becomes minus 1 over 2? I can ask the same question, what is the angle that its sine ratio becomes 1 over 2? Then I put 1 minus to that angle, becomes minus alpha, then I put it there. Does it make sense to you now?
Yes.
Are you sure?
Yes.
Okay. Now, then what is the angle that the sine of it becomes 1 over 2?
Pi over 6.
Pi over 6. Thank you, Rose. It becomes pi over 6. But with pi over 6, Philip, it becomes 1 over 2. But if I put minus pi over 6, it becomes minus 1 over 2. Does it make sense? Yes, Philip?
Yes.
And also minus pi over 6 here. Okay, now, any questions on these ones?
No.
Nothing? Okay, now, this is the time I ask you the very last question. The very last question, which I'm going to ask you now, is this. Okay, and it's going to be this. We say that, okay, now, look at this. We say that sine inverse of, let's say, 1.6. What is that? Which is essentially to ask yourself, what is the angle that its sine equals to 1.6. And I just let me put the boxes here that they are going to be filled. And that's my question to ask it from you. You please give it a try to find this example. How much do you get? You say, find the inverse of sine inverse of 1.6, which is essentially ask yourself, what is the angle that its sine ratio becomes 1.6? Okay, any answers, guys?
Nothing.
There's no answer?
Yes.
Why?
Because the domain has to be between -1 and 1.
Okay, how about you, Philip? Do you have the same idea?
Sorry, sir. I went to the washroom.
Say what?
I went to the washroom.
Oh, okay, okay, no worries. then I want to explain that now. Rose, it was great. Thanks, your answer was great. Look at that, Philip. We said that what is the angle that its sine has to be equal to 1.6. Then you come to here, you see, you find yourself, based on the charts that we provided, you saw that the sine of the x has to always be bounded between -1 and +1. It oscillates back and forth between these two values. Huh? Then when we look at this one, we say the sine of an angle, which we do not know what is that, was equal to 1.6, which is bizarre and ought to say that a human being has 3 eyes. It's impossible. Then sine of nothing can be 1.6. Then it means what? It means that there is no angle that we can think of which satisfies these criteria. Then it means that it's not a valid expression. There is no any angle that its sine becomes greater than 1, because the sine of any argument has to be bounded between -1 and +1. And essentially, that's the thing that we call that. The range has to be between -1 and +1 for the sine of the x. You see how they are connected together? Okay, any questions, guys?
No.
Nothing? Okay, let's see. Now, the thing we plan to do now is to do some plotting. Should show you this property, that the function itself, its inverse transformation, they are symmetric with respect to the y equals to x. That's the thing which is left to be done. Now, in order to do that, I'm just going to go to Desmos, share the screen with you. Let me go to the Desmos. Okay. Guys, do you have my screen now? Not yet, huh? How about now?
Yes.
Okay, if you have my screen now, let me go to this. Okay, you see my Desmos screen, huh?
Yes.
Okay. Now, I'm just going to plot y. Let's call that f of x. Arc sine. In the Desmos, you have to write arc sine of the x. Or also, you can show that with the sine inverse of the x. Look at this plot. You see this? It is. What is the range? This is pi over 2. This is minus pi over 2. And the domain, you see that it's the range of the sine x between -1 to +1. You see that? If this is the inverse of the sine x, whatever you see on the x is whatever was on the y-axis of the sine x, which is the domain is not the inverse, is the range. And now, look at this. I'm just going to plot sine of the x. X equals to sine of the x. Okay. Guys, just only, I'm not going to cut the graph. We are going to focusing on the domain that they are here. Look at these one. And this one, the blue and the green on the domain which they are just connected. You see that they are, if you plot, I'm going to also plot h of x equals to x. I could have changed the color. Since I cannot. Guys, look at that. Y equals to x is the dark blue color. You see that? And you see these two functions, the blue, the lighter blue, and the green, they are symmetric. You see that? The distance from here to here is the same from here. You see that symmetry line?
Yes.
It seems that this area, these two are the mirror image of each other, and also these two things, which it means that the y equals to x is essentially plays a role as the mirror that sine inverse of the x can see himself through the sine x and vice versa. Everything is good for you guys?
Yes.
Yeah? No questions on the plotting, on the seeing the symmetric property of these two plots?
No.
No? Okay. If you have no questions, then essentially it means that we have one task left to do. And guys, please, in the 5 minutes which we have, please go to the school course, school website, and go to the section which I have the course outlines and the success criteria. As a comment, write very briefly what you have learned today. Okay?
Yes.
Awesome. Then essentially it means that we have nothing to do except tomorrow we do the inverse of the cosine function, and we do very cool activity with these functions because they are super interesting functions. Whenever you fill out the form, fill out the segment on the comment section, you can just leave the class and spend the time leisurely. going to stop the sharing. Rose, by the way, are you there?
Yes.
Today we can start the mathematical contest on which is May the 7th. Are you ready for it?
Yes.
You have 1 week for it then, huh? I can also help you. Essentially, we are a team of 2, you and me. Is it good?
Yes.
Philip, do you want to join the mathematical contest?
No thanks.
Okay, no problem. Okay, then Rose, today I'm just gonna get the scenarios of the questions on the challenge. I'm gonna email you one copy of it, okay? Then we can be in touch with the email and messages on the Schoology website. By Sunday night, we have to submit the result back, okay? Then
Okay.
in the meantime, we work together, we find the answers, and we work together to finish it. Good?
Yes.
Awesome. Are you excited?
Yes.
Fantastic, fantastic. Then whenever I just get the questions, I email it to you then. Then whenever you have any questions, you just need some work, just email me. We can stay in touch and work it through together. Then.
Yes.
It's gonna be a great time. Do a challenge in math. Okay, anytime guys that you are done writing the comment section, you can leave class. I will see you then tomorrow then. As long as we are essentially done with the